Optimal control is a popular approach for synthesizing highly dynamic motion. Shooting methods, such as differential dynamic programming, DDP, commonly use L2 regularization on the control inputs in order to minimize energy used and to ensure smoothness. For some systems, such as satellites, the control needs to be applied in sparse bursts due to how the propulsion system operates. We call this type of control sparsity-inducing and modify the DDP algorithm by replacing the control regularization in the running cost term with an alternate loss function on controls. The L2 loss is used to regularize solutions by penalizing the square of the control inputs. It is widely used in optimal control and feature matching in machine learning. In contrast, the L1 loss is used to penalize solutions for sparsity, and as such, it is commonly used for feature selection in machine learning community. Using the L1 loss directly in gradient-based optimization is difficult because of a discontinuity at zero. A smooth L1 approximation combines L1 and L2 losses to get around this problem. The beta parameter is used to decide when to switch from L1 to L2 penalization. The Huber loss function additionally changes the slope of the function using the beta parameter. The pseudo-Huber loss function produces a similar shape to the Huber loss without explicitly switching between L1 and L2 costs. To illustrate the effect of sparsity-inducing cost, we plan the motion of a cart pole on a swing-up task. While this allows us to study application of sparse control regularization terms, it is also a nice demonstration of how sparsity-inducing optimal control exploits the natural dynamics of the system. The L2 loss produces a smooth control sequence. We use the pseudo-Huber loss function to induce sparsity in the controls. The task is still fulfilled while the control is sparse. We analyze the sparsity and the final cost on the cart-pole problem to understand how to tune the beta parameter and the cost scaling. Based on how the cost parameters affect the sparsity and the final cost, we first pick the highest beta parameter according to how much noise tolerance the system has. We then adjust the control cost scaling until the desired amount of sparsity is achieved, while also making sure that the task cost is not too high. We apply the sparsity-inducing cost to satellite control and tune the parameters. We also limit the amount of force each thruster can produce. In general, sparsity-inducing costs, together with control and actuator limits, produce so-called bang-bang control. This is desirable for control of thrusters. We were able to achieve thruster-like behavior to track a multi-stage orbital trajectory on the SSL 1300 communication satellite bus system, the most widely used commercial satellite platform. We see thruster activations at the start and end of each of the stages. Sparsity generally also comes at the cost of slower convergence and higher task costs. This is evident as sparsity-inducing cost terms have less step gradients further away from zero, where the gradient for an L2 loss would be larger. Another application of the sparsity-inducing cost function is to select the smallest subset of robot joints required to perform a task. We successfully applied pseudo-Huber regularization to a kinodynamic optimal control problem on the Valkyrie robot performing a reaching task. The L2 regularized solution exploits 28 robot joints, while the sparse solution only uses 7 joints. The controller is able to track the trajectory using fewer joints much more accurately. We have shown the sparsity-inducing loss function can be used for both joint selection and spacecraft thruster control with the same formulation. On a satellite, we can use the DDP algorithm to plan any feasible sequence of maneuvers by defining a task cost to track a reference trajectory in the state space. Such maneuvers can be used to perform docking or repositioning, which is required for on-orbit construction with a robot arm. The dynamic properties of the spacecraft, any payload, the position of thrusters, and the force these thrusters can generate are taken into account.